We will now introduce an application of the projectile motion principles. In this example, a ball is launched from level ground with an initial velocity of 15 meters per second at an angle of 30 degrees above the horizontal as shown below. Determine the maximum height reached by the ball, the time when the ball returns to the ground, the horizontal distance traveled, the ball's location at t equals 0.75 seconds, is the ball rising or falling at t equals 0.5 seconds, and finally, we need to determine the magnitude and direction of the ball's velocity just before it strikes the ground. So there's the diagram of the ball. You can see that it's launched with an initial velocity of v0, which happens to equal 15 meters per second, and the launch angle is 30 degrees. Now, the first thing we have to do is to locate the Cartesian coordinate system, and we always create a Cartesian coordinate system at the location where the problem begins. So let's introduce the Cartesian coordinate system. There it is. This, of course, is our y-axis, and this is our x-axis, and where the problem begins is defined as 0, 0. Now, again, if this was a package launched from an airplane 500 meters in the sky, then the location of the airplane would be considered as 0, 0. Now in part A, we need to determine the maximum height reached by the ball. Let's start by drawing the ball at its maximum height. So this is the path that the ball would take. It'll eventually reach the ground, and the maximum height is located right here. What do we know about the ball at this location? Well, first of all, it's moving, and it's only moving to the right. So we'll indicate that by introducing horizontal speed lines. We also noted that at maximum height, v sub y equals 0. Again, in part A, we want to find y max. And in order to proceed with all of these problems, it's important to find v0x and v0y initially. I call that prep work in relation to projectile motion problems. So let's calculate those two variables. We know that v0x just equals v0 times the cosine of theta. v0 in our problem was given as 15 meters per second, and the angle is 30 degrees. So we have 15 times the cosine of 30, and that equals 12.99 meters per second. Likewise, v0y equals v0 times the sine of theta. That equals, again, 15 times the sine of 30, and that value equals 7.5. So we know that v0x equals 12.99 and v0y equals 7.5. And I don't introduce units for intermediate results. We only introduce the units when we get the final results. Now, we need to find the maximum value for y. Here's what we know. We know that v0x equals 12.99. We know v0y equals 7.5. And we also know that at maximum height, v sub y equals 0. So with that information, let's go to our projectile motion equations and find a suitable equation. Well, here are the vertical motion equations, and let's examine the first one. It has a y. Can we use this to solve for y maximum? Well, we do have the value for v0y. The problem is we don't know the time that it takes the ball to reach maximum height, so this equation is not useful. How about this one? Same issue. We don't have the time. Not only that, but the y is not contained within this equation, so it's entirely useless to us. How about this equation? We're looking for y, which is contained. Do we have the value for vy? Well, the answer is yes. We determined that vy at maximum height equals 0. And do we have knowledge of v0y? Well, yes, we did that as part of our prep work. Also, g is always known to be 9.8. This is the equation that we will be applying. So here's the equation. Vy squared equals v0y squared minus 2gy. Let's introduce the values. Again, we noted that vy equals 0 at maximum height. v0y equals 7.5 minus 2. G equals 9.8, and we're trying to solve for y. So if we square the 7.5, we obtain 56.25. 2 times 9.8 is just 19.6y. We'll transfer this term to the left-hand side now, and it becomes positive. And if we solve for y, by dividing both sides by 19.6, y equals 2.87 meters, and that's, of course, y maximum. And we've completed part A. In part B, we want to determine the time when the ball returns to the ground. Well, that could be called the ball's time of flight. In order to determine the time of flight, we need to know something about the ball when the time of flight occurs. In other words, just before it reaches the ground. So let's draw that. So I've drawn the diagram. Here's the starting point of the ball. Here's where the ball is about to land. And remember, we're not allowed to let it come into contact with the ground. The question is, what do we know about the ball at this location? For instance, do you know its velocity at this location? Well, the answer is no. We have no idea. Do we know something else about the ball at this location? Well, the answer is yes, we do know something. And that is, we know the y-coordinate of the ball at this location. The ball is about to collide with the x-axis, and the y-coordinate for any point along the x-axis is 0, right? The y-coordinate right here is 0, and we'll note that in the diagram. And this, of course, corresponds to the time of flight. So this is the location that corresponds to the time of flight, and it's also a location where the y-coordinate of the ball equals 0. Now we need to find an equation that'll solve for the time of flight. So let's go and research our projectile motion equations. Here they are, starting with the first equation. We're trying to solve for time. Do we know the value for y? Well, we just established that at ground level, y equals 0. Do we have the knowledge of v0y? Well, yes, we calculated that as part of the prep work. G is always known. This is the equation that we're going to use. So, y equals v0yt minus 1/2 gt squared. Y has a value of 0 right here. v0y, let's find what that value is. Here's the value for V0y. We calculated it again as part of the prep work. The value is 7.5. So we have 7.5t minus 1/2 g equals 9.8 times t squared. Now, how do we solve this type of an equation? Well, let's simplify it first. We have 7.5t. 1/2 of 9.8 is 4.9 t squared. And now we have to rely on our algebra skills in order to solve this problem. So from algebra, what we will do is factor out a t from the right-hand side. And that produces t times 7.5 minus 4.9 t to the first power. Now, in order to solve this equation, we're going to use the zero product rule from algebra. The zero product rule, let's display that off on the side, tells us that whenever we have a product like a times b equals 0, we can solve it by setting a equals 0 and setting b equal to 0. Now, we have an a represented by t, and the b term is represented by the parentheses. We're going to set each of these equal to 0. Now, if we set the first term equal to 0, there's nothing further to do. T equals 0 is one of the solutions. Now, let's set the parentheses equal to 0. We have 7.5 minus 4.9t equaling 0. We'll transfer the 4.9 to the other side and switch the sign to make it positive. And finally, if we solve for t by dividing both sides by 4.9, we obtain a value of 1.531 seconds. Now, which of these is the answer that we were looking for? On the one hand, we have t equals 0. On the other hand, we have t equals 1.531. It turns out that this is the time that we were looking for. By setting y equals 0 within this equation, we basically ask the equation to tell us when is the ball's y coordinate equal to 0. And the equation says the ball's y coordinate equals 0 at time 0 and sometime later at 1.531. And both of these answers are correct. In other words, the ball's y coordinate was 0 at time 0, and it equals 0 later on at 1.531 seconds. We, of course, are interested in the later time. So the answer to this part is the second time. We'll call this the time of flight, and it equals 1.531 seconds. In the next part of the problem, we want to determine the horizontal distance traveled. And the question is, which variable represents the horizontal distance traveled? Let's take a look at our diagram. So here's our diagram. Here is the horizontal distance traveled, and of course the variable that represents that distance is x. So we need to find x. Again, the horizontal distance traveled is x, and we need to find it. Let's examine our equations. Here they are. I need to solve for x, and here's an equation that contains x. The question is, do we know the value for Vox? And the answer is yes. We calculated that as part of our prep work. And do we know the time that corresponds to the maximum distance traveled? Well, that time we just calculated. It's the time of flight. So this is the equation that that we're going to use. So x equals v0x times t, and we found that v0x just equals 12.99 as part of our prep work. The time of flight we just determined equals 1.531, and if we multiply those two together, we obtain a value of 19.89 meters. In part D, we want to determine the ball's location. At t equals 0.75 seconds. That means we need to determine the x and y coordinates. Starting with x. To find x, we can reuse this equation. We have VOX, and now the time is redefined as 0.75. So x could be obtained through this equation. Again, VOX equals 12.99, and the time is just 0.75 seconds. If we multiply those two together, the x coordinate equals 9.743 meters. Now we need to determine the value for y. So again, we have the time, and we calculated VOY earlier. Let's see if we can find an equation for y. Here are the equations. Let's take a look at the first one. Here's y. Do we have VOY? Well, the answer is yes. The time was given, and we always know g. This is the equation that we will be using. So, y equals VOYT minus 1/2 gt squared. VOY we calculated as 7.5. The time is 0.75 minus 1/2, g is 9.8, and the time is 0.75, and we'll square that. And if we enter these values very carefully into the calculator, the y coordinate equals 2.869 meters. So the object's location is given by the following coordinates. The x coordinate is 9.743, and the y coordinate equals 2.869, and we'll label them as x and y, and this is where the ball is at a time of 0.75 seconds. In the next part, we would like to determine whether the ball is rising or falling at t equals 0.75 seconds. So how do we go about making that determination? Well, the answer is, if we just consider what's happening with the vertical shadow, its velocity will tell us whether the ball is rising or falling. In other words, the vertical shadow has a velocity called Vy. If we determine V sub y at this time and find that it's positive, it means that the vertical shadow is climbing, and therefore the ball is climbing. On the other hand, if we calculate Vy and determine that it's negative, that means that the vertical shadow is falling, which also means that the ball must be falling as well. So let's find an equation for Vy and hope that we can solve for it. Here are the equations, and here's an equation for Vy. It equals V0y minus gt. Now, we have knowledge of V0y. We found V0y as part of our prep work. We also know the time. that we're interested in. So this is the equation that we will use. Vy equals V0y minus gt. We calculated V0y as 7.5, g is 9.8, and the time equals 0.75. And if we enter these values into the calculator, we obtain a value of positive 0.15 meters per second. That positive means that the vertical shadow is rising, and it also means that our ball is rising. Finally, in the last part, we would like to determine the magnitude and direction of the ball's velocity just before it strikes the ground. We'll start by determining the magnitude. So the magnitude is designated as v. Of course, that's the final velocity of the ball. And let's search our equations to see if there is something that we can use to determine v. Here are the equations, and the only place that I see a reference to v is right here. Turns out that v equals the square root of vx squared plus vy squared. So in order to determine the magnitude of v, we need to know the horizontal shadow's final velocity as well as the vertical shadow's final velocity just before the ball strikes the ground. So v equals the square root of v sub x squared plus v sub y squared. We need to determine both of these values. Now, let's go back to our equations for a moment. We need to determine Vx, and here's an equation for it. As we mentioned earlier, Vx just equals V0x, which we calculated as part of our prep work. So Vx just equals Vox, and we already calculated it to be 12.99. Now we need to determine Vy just before we strike the ground. And remember, just before we strike the ground, the y coordinate equals 0. So we'll make a note of that. So let's see if we can find an equation for Vy while knowing that y equals 0. Here are the equations. We need to solve for Vy. Will this one work? Well, it should. We calculated V0y. We know the time that it takes the ball to reach the ground. Let's use this equation. So Vy equals V0y minus gt. Now V0y we calculated as 7.5, g equals 9.8, and the time to reach the ground we calculated as 1.531. Let's introduce these values into the calculator, and we obtain a value of negative 7.504. And that, of course, is in meters per second. Let's now introduce these values for Vy and Vx into our V equation. So V equals, again, the square root of Vx squared plus Vy squared. V sub x was calculated as 12.99. V sub y is calculated as negative 7.504. We will square that. Let's now calculate the answer. The velocity equals 15. That's the magnitude of the final velocity. We still have to determine the angle. Now, here's something that's very interesting. The final velocity when the ball returns to the ground equals 15, and that's exactly the magnitude of the initial velocity. So there's a symmetry. In other words, if we throw a ball from the ground at, let's say, 90 miles per hour, by the time, let's say, an outfielder catches it, that ball will strike the outfielder's glove at 90 miles an hour as well, provided that the ball is thrown and caught at equal elevations. Let's now calculate the angle. So step one is to calculate the inverse tangent of absolute value of V sub y over V sub x. So that's the inverse tangent of V sub y was 7.504, and notice that I'm not introducing the minus sign because the absolute value removes the negative sign. Divide by 12.99, and that results in an angle of 30 degrees. Of course, now we have to adjust that angle. Let's note the quadrant that we're in. V sub x has a positive value and Vy has a negative value. So positive x, negative y means that we're in the fourth quadrant. And so for quad number 4, if we look at our angle adjustment table that we developed some time ago, in quadrant number 4, theta simply equals 360 minus the calculator value. That equals 360. We calculated 30 degrees. The angle equals 330 degrees. And so finally we can specify the final velocity as 15 meters per second. The angle is 330 degrees and the units are meters per second. And that concludes this lecture.